Your next presenters will be presenting a cold central plant, a view into our future. Nick Cosenza is a senior pavement design engineer with the Indiana Department of Transportation. He has been there for the past 3 years. His responsibilities include completing pavement designs for roads maintained by the state, as well as assisting the department staff in design, construction, maintenance, and rehab of those pavements. The other speaker is Zach Robinson, a project engineer for the Heritage Research Group. He started there in 2013 as a student intern. Upon graduation from Indiana University with a bachelor's in mechanical engineering, he joined the research group full-time in 2016. Where is Nick and Zach? Oh.
Good morning, I'm Nick Cosenza with the Indiana Department of Transportation. Today, I'm going to be presenting a specific project that we completed last year on State Route 101. This project, we combined a cold central plant as well as FDR for a very successful project. This project was featured in the Road and Bridges magazine and as well won an ARRA award. So a little background about the project on State Route 101. It's located in our Fort Wayne district, which is in the northeastern side of the state. It's got similar climate to Chicago and Cleveland. The project was 8.6 miles long and had about 2,000 vehicles per day with 20% trucks. It's a major collector for US Route 24, and what's unique about this area is that it has a lot of Amish communities. The primary means of transportation for these communities is actually a horse-drawn buggy. And then the project was originally scoped as a single lift overlay, but as we go through the design process, you'll see that this roadway was well beyond what a single lift overlay could treat, and we had to think of other ways that we could rehab this roadway. So that's specifically where this roadway was up in our Fort Wayne district. So this is a picture of just the existing conditions of the roadway. The roadway was very narrow, 20 feet wide, no shoulders. The most common distress on the roadway was actually thermal cracking reflecting from the overlays that we just overlaid on top over the years. It was spaced about 100 feet apart, and each one of these cracks caused a dip or a bump in the roadway, leading to a very high IRI of about 153 inches per mile. On our asset management side, 31% of the roadway was considered in poor condition. In Indiana, we consider a roadway in poor condition when the IRI for a 10th mile is over 170. And then at the same time, the district also had the desire to improve safety of the roadway. With all those horse-drawn buggies and the slow traffic, there's a lot of accidents of cars trying to pass those buggies. So they wanted to add shoulders to the roadway and make it more safe. There's the box area of just some of these thermal cracks we were seeing on the roadway. Over time, this roadway has just been maintained with chip seals. Chip seal over chip seal over chip seal. And these chip seals have had very poor performance. There was a lot of potholes and a delamination of the chip seals. And as we were actually doing our pavement conditions survey and just our pavement investigation, working out there, chips, patching material would actually be tossed up from the passing vehicles onto the workers. And this was just very unsafe out there. And even to maintain a rideable roadway, we had to do patching every year on this roadway. So it required a lot of our maintenance forces just to maintain this roadway. Some other issues with the roadways, we had a lot of rutting on the right wheel path. Rutting was up to 1 inch. The roadway also lacked a crown, which led to a lot of drainage issues. Water would pool in that right wheel path, leading to some hydroplaning, as well as cause a lot of raveling right by that edge line. With any pavement investigation, I'm always going to recommend taking pavement cores. These are very important to be able to confirm what you're seeing at the surface and to answer the question, can you treat these surface conditions with a simple PM overlay or a single lift overlay, or do we need to do something more aggressive and treat the distresses at the bottom? This core is actually very unique in that this boxed area is actually showing a bottom-up crack that we got in our cores. Normally, when you have a fatigued area and you try and core it, the core is just going to come out completely unrecoverable or crumbled. This is just so unique that this is one of the few cases where we got a core and we can see this bottom-up crack. What this crack is showing us is that this roadway probably does not have enough structure, and that as it continues to age and we get more traffic loading on it, we're going to continue to see fatigue cracking on the roadway. And that because of these cracks, a simple PM overlay or single lift overlay is not going to work. Some more cores and some more of the stresses we were seeing, there was a lot of delaminated layers as well as unbound pavement layers. Just the pavement section was no longer working as a laminate pavement section. There was a lot of asphalt stripping due to moisture infiltration, and we had a lot of cracked underlying HMA layers. These cracks will quickly reflect through any surface layer, and we just don't get the desired life out of our preventative maintenance treatments. We also did a lot of non-destructive testing of falling weight deflectometer. The FWD is great for estimating structural capacity of the roadway. On these charts that our research division puts together for us, the blue dots, let's see if I can get the laser. The blue dots actually represent the deflections at the surface, and this red line that runs across, that is what our research division considers the maximum deflections for a structurally sufficient roadway for that classification. In this case, State Route 101 is a collector, and we consider about 12 mils to be the maximum deflections for a structurally sufficient roadway. Of the 150 points we took, 25% of them were at or above that criteria line. So we have a lot of structural deficiencies in this roadway. We also used the FWD data to calculate some stiffness-related parameters of the pavement. We did the elastic modulus of the pavement, which for new pavement is typically around 600, 900,000. Because this asphalt has been out there for a long time, it's aged, it has a lot of cracking. The modulus is very low, about 25,000 or 250,000. And then the structure number is actually is below what's desirable. For a collector roadway, we're actually looking around 4 to 5 for a structure number. We're well below 4 in this case. And then in this area, we have pretty poor subgrade soils. A lot of them are A76 clay soil. The soil is very oversaturated, holds a lot of moisture in it. We get a very, very low resilient modulus numbers on this type of soil. So to summarize our pavement investigation on the roadway, the asphalt pavement on State Route 101, it was just experiencing a widespread age-related distresses and fatigue. This roadway was beyond the point where it was cost-effective to just a simple patch, mill and fill. And at the same time, the district also wanted to widen the roadway to improve safety. So reconstruction became the preferred treatment of the roadway, but we started asking questions. Is there any way where we can reduce the cost of this reconstruction and at the same time reuse a lot of the materials we have out on the roadway? So we opened up our toolbox of treatments, and we decided to look at a couple different recycling treatments and wound up combining them into one project. So the proposed section we came up with was to do a cement FDR to kind of stabilize those subgrade soils. And then we were going to reuse some of the wrap that we had on the roadway to do a cold central plant project. We then capped it with 2 inches of HMA on it. The construction sequence went like this. So this is our existing roadway. We have 20-foot wide asphalt pavement on top of some granular base and subgrade soils. We brought in a cold planing milling machine, which then milled off all the asphalt, brought it off-site to stockpile it. That just left us with our granular base that's been out there since the original construction and the subgrade soils. We then brought in the FDR reclaimer and widened the roadway from 20 feet to 26 feet. And then at the stockpiled area, we processed the wrap, and then we combined it with some engineered emulsion and brought it back to the site and paved it as a cold central plant. We then capped the cold central plant with 2 inches of HMA as a wearing course. With any new idea, you have to be able to prove in some way that it's going to work. In 2010, our research division did a lot of research on recycled bases. At that time, they came up with a layer coefficient of 0.22 for us to use for recycled base. However, since that time, in 2010, Indiana has actually adopted the MEPDG pavement design methodology. So the question became, how are we going to model this material that we've not routinely used in the state or in the nation? So we did a lot of digging into research. We found a very good report, NCHRP 951. That report goes over the material properties for cold in place recycling as well as FDR using asphalt cement. In there, we were able to take the data that they had in the report as well as some of the testing methods and come up with our own dynamic modulus. With that dynamic modulus data, we then plugged it into the pavement MEPDG software as a level 1 flexible layer. So we're treating this cold central plant layer as basically as what we would with a dense graded HMA layer, but it has a much lower asphalt modulus. Modeling of the FDR is a little more straightforward. What we do is we consider it as an unbound aggregate layer, and we give it an annual representation value. What that does is it locks in that resilient modulus year round. And we've done a lot of FDRs in the past, so we had some very good data on the resilient modulus from previous projects in FWD testing. What's great about the MEPDG software is that you can use your inputs to come up with a lot of the predominant pavement distresses of a roadway. And that allows us to compare two different pavement sections and try and design them to get similar lives. For this project, what we did is we took our traditional full-depth HMA pavement section and we designed that first. And then we put in our pavement recycling section and see what the difference in the service life was. And we were able to basically adjust our sections to get a similar design life between the two. In this case, MEPDG predicted that the pavement structure was actually going to be perpetual and that we were looking at structural treatments every 12 to 15 years to maintain that smoothness as well as reduce environmental aging. One thing to note is that the MEPDG software is not perfect. It requires a lot of data, a lot of calibration to get perfect results, but it's the best tool we have right now. And one thing to note is that at InDot, we do have local calibrations for rutting and for total rutting and AC rutting. So if you use just the global calibrations and try and input some data, your results will be different than what I've shown. With also any new idea, you have to show that there's some cost efficiency with it. On the left here, we have the reconstruction with the asphalt recycling. What that consisted of was asphalt milling, the cement FDR, cold central plant, and the HMA surface. In total, all those items combined was about $28 per square yard. All those prices are actually right from the unit bid tabs from that project. On the right, we have our traditional full-depth HMA section. What we do traditionally is just some chemical soil improvements, a 6-inch granular base, and then 7 inches of HMA on top of it. Adding all those up, it came out to about $44 per square yard. And those prices are based on weighted unit averages across the whole state. In total, by using this recycled section, we were able to reduce the cost of this project, of the pavement items, by about 33%. And this is very important, especially on our collector roadways, they're not as high a priority as our freeways or our interstates. So anything we can do to reduce cost goes a long way on these smaller 2-lane collector routes. And then the last step of this design process was the advertisement. At the same time as we were doing the design, we finalized our specifications. We looked at a lot of other DOTs as well as the ARRA guidelines. And then once we put this out for bidding, what surprised us the most of the project was actually how competitively this was bid. In the area, we have 2 main prime contractors on it. And the difference between those 2 bids, this material they've never used before was only $50,000. So we were very surprised to see how competitive it was bidding-wise on this project. So now that we've made it through the design process, I'm going to turn it over to Zach Robinson, who's going to talk a little bit about the mix design and construction on this project.
Okay. So the first thing, once the project was awarded, we actually went out and did mix design sampling in order to obtain materials for mix design. Through that, we did verify some of the distresses that Nick talked about, a lot of the longitudinal cracking, transverse cracking, and that really bad chip seal bleeding that you've seen in the pictures. When we were actually taking our cores, one of the things that we really looked at were, again, like Nick mentioned, the full depth cracking that or the bottom up cracking that we saw in the bottom left picture there, as well as the delamination and stripping throughout. The asphalt binder, the asphalt mix thicknesses ranged anywhere between 8 and 13 inches with an average of 10.3 inches. Oh, wrong button there. So the cement mix design was actually performed by Alt and Witzig Engineering per Indiana Test Method 595. They actually performed 2 separate mix designs. The first one was actually the minimum percent passing the number 4 sieve that they experienced on the field. The second was the maximum percent passing the number 4 sieve that they observed on the field. Based on the specification as well as the planned overlay, a minimum unconfined strength of 300 psi was required for this project. And ultimately, Alt and Witzig recommended a 5% cement addition rate for the cement FDR. Heritage Research Group performed the CCPR mix design per Indiana Test Method 592. 3 different mix designs were performed at the 3 gradation bands in which are actually laid out in Indiana's test method. The minimum dry Marshall stability there was 1,250 pounds. As you can see, all the tests actually passed, and ultimately a 2.5% emulsion was recommended for the cement the emulsion CCPR. So once those designs were actually done and approved, the actual construction began. The first step was removing the top 8 inches of the existing asphalt pavement, where it was hauled to a nearby stockpile that was about 10 miles from the project. There it was crushed to meet 1.25 inch minus gradation. During that process, utility work was being performed, and also the cement FDR was started. As you can see, a specialties company, one of the ARRA members, actually performed the cement FDR work, following InDot's recurring special provision 307. After the cement FDR was cured and had been proof rolled, the emulsion CCPR construction was actually able to begin. Asphalt materials supplied the engineered emulsion, and pavement maintenance system actually produced the CCPR mix. Local contractor, Brooks Construction, was actually the one that laid that CCPR mix. And ultimately, in order to pave that almost 9-mile road, 37,000 tons of CCPR mix were produced across 16 days, roughly at about 300 tons per hour. During production and prior to production, actually, HRG did do some mix design verification on the materials. So the red line there is shown as the specification minimum for dry Marshall stability. The blue bar there is the mix design stability that we obtained during the mix design process. The orange bar actually is wrap that was sampled after the crushing and processing of the wrap that was then laboratory coated and laboratory compacted. The gray bar actually is a plant-produced mix that was sampled during production and brought back to the laboratory, where it was then compacted and tested. So, following the CCPR construction and its ultimate curing, the roadway was milled in order to ensure cross slope and ride. And then it was a 2-inch, 12.5 millimeter surface mix was overlaid onto the road. And that pretty much wrapped up construction. I'm going to hand it back over to Nick to talk about some of the testing that InDot performed.
So during the design process, we did have to make a lot of assumptions on this material. So we were very anxious, once it was all completed, to do some testing on it to make sure that what we assumed in the design phase is actually what we got at the end. So what we wound up doing once it was completed is we tested the FWD again, as well as IRI, rutting, and cracking. A lot of the IRI, rutting, and cracking data, I mean, at this point, since it's a brand new roadway, is actually really good. But what we're going to do with that data is we're going to take, basically go across the roadway again every year, and we're going to basically use that data to verify what the MEPDG output was. And in the future, with more projects and more data, ideally we'd be able to develop some local calibrations for the MEPDG software. But for now, probably the most important stuff to look at was the FWD testing. What was very surprising, that what we got on the FWD testing, is that the cold central plant and the FDR at this time provided some very consistent results. We took 150 points across the roadway, and we went from 25% of the roadway that had structural deficiency to only 2 points. I'm going to highlight these 2 points here, so they're both right there on that side. The first one right here, what we predict is happening there is that we actually got a subgrade issue. The blue dot is the surface deflection, and the green dot is the subgrade deflection. And because they're going up at the same rate, what that usually means is we got a subgrade issue there. So that's just one spot where we didn't get with the FDR very well, and we're just looking at a subgrade issue. And then the spot right next to it, another point, that's the subgrade point there isn't going up, so we're expecting there is some construction variability. But for a 8.6 mile roadway, only 1 point being above that criteria line is very good. Below it, we have our back calculated results. The most important thing here is that because we have a thin lift of HMA on it, the software can't actually distinguish between the cold central plant mix and the HMA. So they had to combine the modulus of the asphalt with the dense grade mix and the cold central plant together. In the end, the results were much more than what the aged asphalt was, but it is a little bit less than what new asphalt is. And then the modulus of resilience for the FDR is actually over 100,000, which is well above what we put in our software on the design side. And then the most probably important output here was actually the structure number. On collector roadways with about 7 inches of HMA, we're looking at a structure number of 4.5 to 5. With FWD testing on this recycled section with 6 inches of CPR, 2 inches of HMA, and that FDR underneath, we actually got a structure number 5, which is on the high end of what we expect for this roadway. So this roadway, the structure number is more than adequate for the truck volume on the roadway. And that was what was very impressive about it, was that this section that was 33% cheaper than our traditional construction gave us the high end of the structure numbers that we were predicting with our traditional reconstruction. So in the end, we are very proud of this project. We're very excited about the results. And in the future, we're looking to do more types of these projects. So thank you very much. And if there's any questions.
Sorry if I missed it, but how long after the project is complete do you do the following rating testing?
So the question was, how long after did we wait to do that testing? We did the testing just a couple months after it was completed.
How do you determine the modulus of resilience?
That would be a good question for our research group that's not here. From there, it would be, they would have to distinguish it out from the sensors. I can't give you a great answer on it because I don't actually produce the results. I can give you the email of our research group, and they could tell you what process they use to distinguish it.
Nick and Zach, great presentation, and this is really important information to have. I want to commend the thought that you guys have on doing the continuous performance monitoring of this section. That information is really needed. One thing, I don't know if you have the ability to do, if you have a similarly, let's say, reconstructed section using a non-recycled option versus a recycled option, if there'd be a way to do any performance comparisons between the two, especially something along the lines of the same structural capacity. I have a feeling, given that the stiff foundation you've got with that FDR in there is going to provide superior performance even at the same structural number than a non-recycled design. But it'd be interesting to quantify that if you could.
Yeah, that's a great idea. Thanks for that info. I'm going to write that down. I'm going to do that right away when I get back, because that's a great idea. Thank you very much. Let's go in the back over there.
Yeah, when you widen the shoulders, did you take any precaution? Did you engineer any shoulder material out there? Or did you just push material to the outside?
So this was actually one of the lessons we learned on this project. In this case, we just kind of used the material that was out there, which was stone-ish, stone subgrade that's just combined. So what we learned from it was the milling, or the reclaimer doesn't actually move that material around very well. So the outside shoulder did have some issues of weak areas where we had to reprocess. On our FDR projects that we have gone forward with, we're actually removing out where we're widening, and we're bringing in usually wrap or a corrective aggregate to fix that up. Create a homogeneous section all the way across.
I have a question about the cost. You showed a spreadsheet, which is really nice comparison. And that was the engineer's estimate, I believe?
Yes.
Okay, and after the bid was done, project was constructed, what were the costs like? Were they comparable, what you had in mind?
So on the engineer's estimate, we were a little bit low. We were about 5.5 million, and the bids came in at about 6 million. We were actually a little bit off on our quantities, the quantities of the emulsion. So during construction, there wasn't any change orders or anything, so it came in pretty much at that bid price. There was no major issues with it. And then just to give you background, our traditional reconstruction cost is about $1 million per mile on these collectors. So we would look at about 8 million for 8.6 miles. So the total project was reduced about 2 million from what we expected. Back there.
Can you talk about the traffic control a little bit? How was traffic, the staging?
Did we close this one, Zach?
Yes.
Okay.
Yeah,
Thank
so
you.
during construction, the whole roadway was closed for this particular project.
Any other questions?